Welcome to the last section on graphs. This is also the last section in the chapter, and this is also the portion that you need to be able to do your final homework. So this section deals with what we call directed acyclic graphs. Directed acyclic graphs, right? Well, they're directed graphs, okay? What does acyclic mean? Acyclic means there's no cycles in it. So directed graphs that have no cycles. So we're going to be covering directed acyclic graphs, and we're going to be covering topological sort, which is a sorting algorithm essentially that we can kind of do on a directed acyclic graph. It's a bit different. It only really applies to graphs. So the interesting thing about directed acyclic graphs is that they have a whole lot of different properties, but the primary one is that when you go through a node, you cannot go back. Once you go to a vertex, you can't get back, right? And we use this for a variety of purposes. One, which you can see right here, is that we use it for course prerequisites. So, for example, you have to take Calculus 1 before you can take Calculus 2, or the CIS 067 and the 066 course. And you have to take both 067 and 066 before you can take 072, and so on and so forth. So this is a course flow chart. Now, what topological sort will allow us to do is basically give us an ordering in which we can take these courses. And the difference between topological sort and a bunch of other sorting algorithms is that there's going to be a bunch of different ways you can sort something topologically, right? There's a bunch of different possible orderings depending on the graph, but so long as they follow a specific property, all those are valid. Here's an example of another directed acyclic graph, something that's a bit more abstract, right? Notice that all routes lead from 0 to 8, right? So this is another property of a directed acyclic graph, that all paths will eventually lead you to some kind of sink, right? Everything will eventually go from one node to 8 over here, right? So this is another directed acyclic graph. Right, we could go 0, 4, 7, 8 to get to 8, or we could go 1, 5, 7, 8 to get to 8, right? There's a bunch of different ways. Now, a topological sort is an ordering of all the vertices in a directed acyclic graph. So it's a way that we can order all these nodes. And the ordering has to be such that if there's an edge between the first node and a second node, right? If there's, for instance, a edge between 0 and 4, then 0 has to be before 4 in our ordering, right? That'll make sense in a bit. So this will be true for all edges. So long as there's many valid different paths to get through a directed acyclic graph, there's going to be many different orderings. If there's only one way through a directed acyclic graph, then there's only really going to be one ordering. And that will be the case in your homework. So, for instance, going from 0, 1, 2, 3, 4, 5, 6, 7, 8 is a valid ordering in a topological sort. Why? Because 0 comes before 3, 4, and 1. 1 comes before 4 and 5. 1 comes before 2 and 5, right, in this sorting. Right? There's an edge from 1 to 2 and 1 to 5, so 1 comes before 2 and 1 comes before 5. 4 comes before 6 and 7 in the ordering because 4 has an edge before 6 and 7. This is also a valid sorting of this. 0, 1, 5, 3, 4, 2, 6, 7, 8. So let's just think about that. 0, 1, 5, 4, right? So 0 to 1, 0 to 4, 0 to 3. 0 comes before 1, 0 comes before 4, 0 comes before 3 because it has edges going from 0 to 1, 0 to 4, 0 to 3. So 0 to 1, 0 to 3, 0 to 4. What wouldn't be and then let's see, what else would be valid? 4 to, so if we instead swap that with that it was 0, 1, 5, 4, 3, that would also be valid. However, if we were to swap, for instance, 0, if we were to make this, for instance, let's say 0, 5, 1, so if we were to do 0, 5, 1, well, there's an edge from 1 to 5, but in our ordering, that we just declared, 0, 5, 1. 5 would come before 1, so that wouldn't be a valid ordering. Okay, so let's go ahead and ask. So hopefully you understand that. Let's go ahead and just write down a couple more different. We can kind of eyeball this and write down a couple different sorts for this, different orderings. But let's go ahead and write down some more and see if they're valid. And then we'll see how to. And then in the next video, we'll see how to generate these topological sorts, right? So let's go ahead, and we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, right? That was a valid ordering. So now let's go ahead. If we move 0 to be between 2 and 3, that's not a valid ordering, right? Because in our example over here, right, 0 has an edge between, there's an edge between 0 and 1. In our ordering, 1 is before 0. That's not gonna work. Furthermore, 1 is, so what if we did this? 0 to 1? Well, again, 2, there's an edge between 1 and 2, so that's not going to work, right? It has to be 1, 2. No. Right? So what would be a valid topological ordering? Okay? Well, a valid ordering would be, let's say, 0, 3, 1, 4, 2, 5, 6, 7, 8. 8 will always have to be at the end of any valid ordering, because it's the last node. So 6 and 7 will have to come before that. They'll have to come before 8, and then 8 will have to come. And then all the other numbers will have to come before 6 and 7. Although there's no problem with us swapping out 7 and 6 like that, right? But we have the node between. We have an edge from 0 to 3, 0 to 4, 0 to 1. So that's fine. Then we have an edge from 3 to 6, and 3 to 4. So that's fine. 1 to 2 and 1 to 5. So that's fine. 4 to 6 and 4 to 7. So that's fine. 2 to 5. So that's fine. And then 5 to 7, that's fine. And then 6 to 8, that's fine. And of course 7 to 8. And then 8 goes nowhere. So that's a valid topological sort.